All right, I'm sharing this with you. I hope you can see that.
Yep.
All right, now by the way, if you need to take screen captures and you want to like frame these and hang them on your wall, I will admit this is some of the best art you'll ever look at. Okay, I mean this is Rembrandt, Rubens couldn't do this. Anyway, a lot of this you know, but we have to lay the foundation so that you'll understand what you're doing when you start doing the big tweaks. This is a very simple diagram of one of the oldest methods used in some of the early limiters and compressors. A simple voltage follower. You see, you got your audio coming in, and you can't see my mouse pointer, right? Okay, yeah, just making sure.
Your mouse. Yeah, we can.
Okay. All right, and then this, you'll notice it's following. Now, one important thing to remember is he's following the peaks. He's following the peaks. And incidentally, on these older models, the attack and release time, which we'll get to in just a moment, were basically set by resistors, the resistor time constant. All right, why won't it change pictures? I can make that happen. Watch this, because I'm fierce. Oh, I see what it's doing. The pictures are covering. Here we are. This is a good, by the way, I don't know if any of you guys ever play with spice modeling, but I use it a lot. I use a free program that, well, they belong to Analog Devices now, but it's LT, Linear Technology. It's called LT Spice. It is absolutely free, and it's one of the best things you'll ever play with. It's going to be loaded with their components. I mean, you see LT156s are the operational amplifiers I'm using. But you can actually play with things, and you will learn things. I promise you. You'll go, hey, now I understand why that sounds like Dookie. But anyway, you can see I've got the, I say signal out. That's actually a pulse input. We go through a precision rectifier, and then there's your actual control voltage. The attack time is going to be the time constant of a 100 ohm resistor with 2.2 microfarads. Release time is going to be 2.2 over 100K. We're assuming that the load there is going to be a very high impedance, which it would. In real life, what I would do is immediately follow that up with another op amp to buff it. But here's what I want you to see. Notice with that relatively quick attack time, I've still got a little bit of slope right there. Because it does take it a finite amount of time to react. And then as soon as that pulse lets go, the capacitor starts discharging, and there goes the voltage down. All right, why does he show you this? Because of the time involved. Now, I know everyone's thinking we use these fancy, super awesome, blinky light covered digital things now. Well, I've got news for you. The software that they put in those, most of it is based on this old technology, all the way back to the very first limiters. Why did he go to, oh, this, I love Windows. I'm being very facetious, very sarcastic. I mean, you try to work in Windows and you're constantly get, do you want to update Adobe? No, I don't. Anyway, I hope you're not hearing those bombs. Oh, he wants to restart because he put in updates. No. All right, we've got peaks here and regular audio level, and you can see this is a typical compressor that uses a fast attack and a slow release. Incidentally, you'll notice in this case the attack's not quite fast enough, but you can see when that big peak bangs in there, we get what's called ducking, followed by a slow release. We mentioned that last time, and the reason I'm showing you this picture is because understand that even on a modern multi-band processor, you are essentially adjusting a whole bunch of these, just divided into different frequency bands. So that's important to keep in mind, and that's why I'm showing you these. The reason we do the multi-band is because it's less likely, for example, a kick drum, which is what that models, is only going to duck the bass channel for a second. This also, you'll see any of you guys use an older process, and I'm going to get to the symmetrics in a minute, by the way, because I think he's very interesting. Can't remember who it was, said they have a symmetrics mic processor. If it's a 560 series, oh, hey, okay, 560 series, it's analog, right? You can just nod your head. Okay. But anyway, this shows you, this, by the way, is 3 notes on the piano. Middle C, do, re, mi. Notice the envelope follower, which I always just call fast attack, slow release. Notice how he's really following the peaks. This is the RMS, root mean squared, which is, you know what RMS is, you're engineers. You can see this is a lot smoother. But now what that tells you, if you're using this control voltage to control level, you're going to have some overshoots at the beginning. So if we go back to the previous picture, what we're going to do in any limiter on any band, whether it's a broadband or a multiband, we're going to use the compressor to control the average level, but we need to control it well enough to avoid a lot of peaks. Because what we're going to do with the peaks is we're going to have to clip them. Otherwise, we'll overmodulate, and you end up turning your transmitter down to where you don't get any loudness. This, by the way, is a linear technology chip, the 1966. I used it to generate an RMS trace of a little bit of guitar. You can see again that the RMS tries to follow, I say average, you know that's not accurate, but you also know what I mean. It tries to follow the average power. And incidentally, the people who design, whether it's an analog processor or the fancy digital stuff that's emulating RMS, they've got to do some very fancy things to work around the fact that that capacitor size, which that's what sets your time constant, which with RMS it sets your averaging constant. If that's too small, it's going to respond a lot faster, but you get distortion at low frequencies. If it's too long, you're going to start getting ducking because the release time is going to be too slow. Even RMS, while it theoretically and mathematically does not have an attack and a release time, in real life, it's going to have, I guess we'll call it response time. 2 more waveforms for you. Hold on 1 second. The originals are shown at the top. They're identical. And I've shown now with an RMS compression, you'll see that I've got 2 kind of peak areas at 1 and 2. Not surprisingly, the RMS misses the first peak. Then he starts getting a handle on what the energy is. And so by the time that second peak comes along, he's reduced the level. Then you get a little bit of gain boost here in the middle. And you can see the RMS is a bit smoother. But now I want you to keep in mind, if we're going for maximum volume, we can't just clip here. That's going to be distorted. So we're going to want it to be pretty aggressive as far as attack, release, or averaging time. And by going multi-band, we can do that. Let's look here now. This is a good old standard fast attack envelope follower. You can see now the very first peak that gets through, the transmitter ran screaming out the back door of the building on that first peak because it probably hit 300%. Then it instantly catches and starts controlling the second peak. You'll notice that depending on the release time, I'm increasing my level here at 0.3. There is a little bit of an overshoot right there whenever suddenly the gain goes up again or the volume goes up again. There's going to be a little overshoot while that attack time prevents it from reacting instantly. But you can see, while I'm not saying that the RMS is better than this or vice versa, you will see that it is a little bit easier to clip this. And by going with multiple bands, we can optimize the attack, release, and or RMS averaging for that particular band. I got waveforms out the wazoo, Mike. This is another example where I brought in some, I need to see the name of the file, and here it is. This, how many of you remember the old Volumax? The original Volumax used diodes for gain control. And I'm not going to bother telling you this whole circuit here, but basically we take the input and we sample it, and then we rectify it and we use it to forward bias some diodes. If the signal is higher, we've got more control voltage, which forward biases them more, which is going to reduce the input signal. Biggest drawback to that is these are only linear over a relatively small range, and if you go past that range, distortion becomes absolutely horrible. But as you know, if you've ever heard of Volumax, it does keep the level very constant. You see that. Even this low-level stuff here, look how it just pumped it up. All right, and this is a little opto compressor circuit that I built. It's fun to play with. By the way, I designed this for guitar, so I wouldn't necessarily want to put it on, if you're playing Beethoven on your classical station. But got the audio coming in once again. A little bit asymmetrical there. I think we had a DC bias issue, but you can see that it reduces the gain or holds it constant on that loud passage. On the lower passages, it's pushing them up. All of this is expected, and you already know. Now, interestingly enough, DBX, years and years and years ago, developed something called the Blackmer VCA cell. You may have heard of it. The Blackmer cell. I think it was named after one of their guys named Blackmer. DBX then sold their semiconductor division to a group of their former engineers who formed a corporation named THAT. And this is one of their processor chips, one of their voltage-controlled amplifiers. It's the 2180A. And the reason why you might find this interesting is because if you have a DBX 1066, any of their older analogs, or if you have symmetrics, it uses this chip or one of these types of chips from that corporation. Now this one, I'm not doing a compressor. I'm just showing you the gain control. You can see we have a constant 100 millivolts peak going in. This is the gain control voltage. It's negative means reduce the volume. If I were to put positive in there, it would increase the gain. That's the other reason why a lot of people liked these back in the analog area, because they were so flexible. But you can see as we increase the negative control voltage, we're subtracting gain. And sure enough, see that? It drops down, which is to be expected. Now, I can't believe that I really need to show you this, but I just want to make sure. Remember that decibels are decibels. They're nothing but a ratio. If you're comparing powers, you're going to use the 10 times the logarithm. And if you're using voltage or current, you use 20 times the logarithm. Or if you do like virtually all of us do nowadays, you use the calculator on your phone. Makes it a lot easier. Now, let's get to a symmetrics. I think this is basically based on the 565E. But remember, they use the same Blackmer cell and the same control circuits in most of their analog products. You start with an expander. Some people call this a noise gate. an expander, noise gate, or they'll just call it gating. The original noise gates would basically slam shut, open up very quickly because the attack time was extremely fast. And then depending on your release time, you would actually have a little bit of noise until the expander finally closed. To answer your first question, you're going to set this by ear. First of all, don't expect this thing to work miracles in a noisy room. It's not. Try to get the mics as close to Talon as possible. Try to have a quiet room if you can. But what little bit of hiss you got left over from computers running, air coming out of the ceiling, whatever, use this to smoothly expand down the noise and help hide it. And that is a matter of taste. You set your threshold. I'll show you in a minute when I show you some curves. I'll usually set that. I listen to the compressor. I'll crank it up so that I can hear the noise, and then I turn the threshold just to the point where it starts eating the noise. And I might go a little bit higher than that. I might turn that just a little bit more. Then you set the ratio for whatever sounds natural. 2-to-1 is a good place to start. 4-to-1 starts being very noticeable. 10-to-1 is, to most ears, is going to start sounding like a brick wall. You're going to have an old-fashioned noise gate. You might as well use a relay. And here you see how expanders threshold work. Everything above, I've set the threshold to -20. Everything above that is at a 1-to-1 ratio. There's no compression, no expansion. It's a piece of wire. Audio goes straight through. Anything below threshold, in this example, I've adjusted for a 1-to-2 ratio. So you can see at low levels, I've really reduced. Look at this, at a level of 60 dBm in fact, you've got the threshold. That is going to be the threshold at which it begins compression by this ratio. You can set the threshold where you want it to start compressing at that ratio. And by the way, since you're actually using a VCA to lower the gain, you're going to need some makeup gain. You're going to need some makeup gain because you're going to lose some signal in here. You've got to make up, and they may not label it that. It may just say output because they haven't. They don't have any imagination. They're geeks. Here we are. I'm showing you once again threshold up to 0 dBm. I'm 1-to-1, piece of wire. Cannot tell a difference, with the only thing being, if I do have my expander, I've reduced noise, which may in and of itself be a good reason to use, for example, your mic processor. Might be a good reason to use that just to get the noise down while still having dynamic range. Then you can set a threshold. Set to 10-to-1, we're really talking about more limiting than compression, just because somebody will get excited. I can't believe you said that. No. And every meter in the station is pinning in the red. 2-to-1, of course, would be more gradual. Let's keep looking. This is going to be in software on your digital processors. This also is something you normally don't have any way to adjust. But that's a soft knee. And by the way, again, I'm not going to go back to that schematic of that VCA, voltage controlled amplifier. But if you want a little interesting trivia, the way THAT, the way the air engineers get a soft threshold, they simply put a diode in the control voltage because a diode is nonlinear. Whenever I saw it, I couldn't believe it. I said that is so simple. A diode in the control voltage. There you go. And then finally, we've got our limiter, clipper, whatever you want to call it. His purpose is to chop off peaks or to reduce peaks so that you don't overdrive your transmitter or your recording input or whatever this is feeding. Common sense, I know. I don't mean to, I don't mean to belabor the point because you know a lot of this. I just want you to start visualizing what's actually happening in a single band of your Omnia 11. Because this basically is what's happening in that single band. And you probably know you could overdrive an old tube input and it wouldn't be too bad unless you really drove it hard. Overdrive solid state input could be bad, especially older germanium transistors. It could be pretty nasty sounding. You overdrive a digital input, it's going to go insane. It goes into what the programmers call undefined behavior, which basically sounds like hash. You know this. If you've ever overdriven a digital input, you might get sputters, you might get dropouts, you get breakup. There is nothing pleasant about it. So you want to spend a little time here, even in your recording rooms, even in production and imaging. You want to make sure you've got some smooth clipping to prevent driving that input. And you do know, by the way, on any processor like this, you always put a tamper shield over it, right? Even if it's just a piece of cardboard taped over the front so that they can't adjust the knobs. Because any talent gets at a processor of any kind, they're going to try to turn themselves into the monster truck man because they think that sounds so good. But you got to watch this makeup gain. You'll get a louder sound by turning that up and cranking the drive into the limiter or clipper, but you obviously increase your distortion. So that's a judgment call. Here's the total unit, threshold of compression. There's your threshold of expansion. Notice in this particular adjustment, I've set it up so that between minus 40 and minus 20, we're a piece of wire, no change. Above minus 20, I start compressing. Looks like about a 4-to-1 ratio. Expansion below 40 dB, that's about a 2-to-1 ratio. Helps lower my noise. Now, I'm going to show you some pictures. I've got to pull them up. I'm going to show you some pictures of a Symmetrics processor in a minute. You can do this if you don't have dedicated mic processors. You can do this, use a dual mono processor. It's very important. On any stereo processing, if you're going to maintain the stereo image, if you're going to hold that image where, like when in the recording studio, they put the flute over here, they put the trombone over here, they put the drums in the back, vocalist is in the front. They do that with pan controls. I mean, unless, it's a really high quality concert and they're using a stereo mic technique. But in most cases in recording studio work, they're going to pan, the pan controls, fading left or right in the studio. And so you've got to make it so that, for example, if our trombone over here is currently blasting out a solo and just having a ball, you can't pump this side up. You can't increase the gain on that side, or it's going to move this. Everything's going to be moving around in the stereo image, and not in a good way. Basically, you're going to destroy the stereo image if you don't use linked processing. And that can be, in these older analog processors, that can be as simple as the control voltage. You sum both channels together. You just take the control voltage from both channels together and use that to control the gain of both channels. And what that means is the loudest channel is going to control the gain. Make sense? You see what I'm saying? Now, boy, that looks familiar, doesn't it? That's not your mic processor, but that is the 565. I forgot to mention one interesting little tidbit that now I think DBX did this, and I'm pretty sure Symmetrics did it. It may interest you to know that they actually only use one VCA for each channel. But they put all their sophistication in the control voltage. they actually have a very smart control voltage circuit. It's pretty well designed if you can get your hands on a schematic, which is not easy to do. You'll see that it responds differently to very fast peaks than it would to a very slow peak. You'll see it responds as to gradual changes, completely different from quick changes. It also takes care of the expansion. It looks at the overall level and says, yeah, we're getting kind of low now, and so it lets the expander cut on and reduce noise. Notice on this metrics, all we can adjust is the release. And they don't let us adjust the attack time on the compression either. I guess they feel like we can't be trusted with it. But there's your ratio. And I think, yeah, it goes to 10. Ours goes to 11. Then you got the threshold here, which is where you want it to start. And the reason you're going to want to check your input level and your thresholds and all that, this one doesn't have a makeup game per se. So what's going to happen as you turn the ratio and your threshold down, you're going to be lowering the level into the limiter. This is a very important point that I made in the original SBE processing course that we put online. Your compressor has to do a good job at holding the level constant, as natural a sound as possible. But he's got to hold that level reasonably constant. On the other hand, you don't want too much processing in there. You don't want him reacting to transient peaks because that gives the limiter nothing to do. I mean, unless you're in audiophile mode and you really, really want the highest possible quality, you're going to turn the limiter up to the highest possible threshold so that it never does anything and control it all with the compressor. But you want your compression to hold that level constant, but yet you still need to leave the limiter something to do. Here's that all-important stereo link button. This is what I was talking about. If you're going to be using this as two separate mono processors, make dang sure you push in dual mono. Otherwise, make sure you are in linked stereo mode. And again, the reason is because if you got one host who is very, very loud and another one who's soft-spoken, all your listeners is ever going to hear is that loud. That's all they're ever going to hear is the loud guy. I said all that to say this. Does that look familiar? Understanding that basic foundation, you can now understand what is happening in your multiband processor. You could actually build a multiband processor with 3 of those symmetrics units. You might want an extra, like a Volumax or something, to take care of transient peaks, but simply use a crossover, bass, mid, and treble. Feed it into the 3 different symmetrics, mix them together. You can use an old mixer sitting around in the junk room for that, and then put it into your Volumax to protect your output level for overmodulation, and then out to a transmitter or recording, whatever you're doing. So that's the reason why I went over all of this, because I wanted you to see that. All right, let me cut off full screen for a minute. Yeah, shared window is closed. Okay, it says I'm no longer sharing the window. Hopefully that's right. Found a photo for this meeting. That's interesting. Oh, let me pull up the chat window. All right, a photo for this meeting. Let me see what he's got here. Oh, yeah. There you go. Let me share the screen on that. Maybe Anthony can tell me. There it is. Maybe Anthony can tell us what we're looking at. Obviously, it's a whole bunch of them, whatever it is. Let's see. What are those? I can't make it out in this picture. There's something. Can you guys still hear me? I want to make sure I haven't killed. Just nod if you can.
Yeah,
Thank you.
we can hear you.
Anthony doesn't have a mic today. That's why he's not responding. He's responding in the chat window.
Well, you tell Anthony I said a real engineer would have a mic.
I think he can hear you.
Okay, Anthony, a real engineer would have a mic. All right, let's undo the screen sharing. Let's get done with screen sharing. Okay, let's close that. There we go. I see CBC Toronto, 64 stations at a time. Yeah, you would have a bunch of processors. TC, who is TC? I am terrible with acronyms and abbreviations. That is an interesting picture. TC is TC. Boy, that just cleared it right up. I assume they're a processor maker. Believe it or not, I've never heard of them. Oh, from Denmark. Okay. So you use Farron stuff. TC Helicon. Thank you, Anthony. Believe it or not, I've never heard of them. Proof that I don't know everything. That's one I've never heard of. All right, this is going to take me just a moment. If you guys, believe it or not, I got to take a very, very quick break, and I'll be right back. Okay, let's see if we can take a look at this. This is one of my actual processors in operation. This particular station does religious programming, so there's a lot of talk, a lot of preaching. But this is a good introduction. This is a multiband. This, as you can see, is the Wheatstone FM55. That's the particular one, which, by the way, if you need a reasonably priced analog FM processor, if you're not running HT, this thing is sweeter than sugar. It will get her done. All right. You see, I feed it with a, yes, input fail-safe. I do have a backup analog on it. All of that's pretty much just straight-up engineering. You know what to do with that. Phase rotator, I don't know why I'm using that, but it just made me happy. Unless I need to look at the manual. That may be one of those that can detect if your left and right channels are out of phase, in which case, that's a beautiful thing. Because you put left and right channel out of phase, and all of a sudden your people listening on a mono radio are going, where'd the station go? All right. Parametric EQ. All right, we're going to start talking about how we'd like to adjust this. Frankly, I think that's a little too low, but I'm using one of their presets, so I'm not going to touch it. We're boosting by about 2.5 dB on the bass. We're flat in the 200 hertz, which I call that mid-bass, low mid-range. 749, which is right square in the mid-range. We've got a little bump on it. Now, that might strike you as odd. You know, why do I want to bump the mid-range? Because isn't that going to make it sound, honky or boxy? Not really. Because one of the other tricks you can use, especially, we mentioned one time before, if you are forced to use an older processor on a web stream or on an HD channel, you may have to roll the highs back a little bit. In that case, I wouldn't do it at 750 hertz, but I might roll the highs back a little bit, and I would add a little bit at, say, around 6 or 7.5 kilohertz to compensate. You'd be surprised just a dB or two here and there will make a big difference. For the most part, though, you need to stay away from the parametric EQ, except for very small adjustments. These, by the way, like I said, they were done by Wheatstone. I'm using one of their presets. I made some changes and saved it, which is why it's under a different name, but that's basically one of their presets. Then the multiband leveler, that's your compression for each channel. And you can see we've got 5 bands. And it's showing what he's doing. Notice it must be voice, and I'm guessing it's a female because you'll see he's pumped up the gain on the bass because there's not a lot of bass content, but there is a lot of mid-range, so he's cutting the gain on those. Here again, these are your crossover frequencies. If you change these, be sure to save your current preset so that you can get back to what you're doing. In most cases, you're going to find a preset that's close to what you want and then make very tiny changes, a little bit at a time. And then there's AGC attack, return to 0. That's a form of gating. That's what they call their that's what I guess they consider their gating. Notice the threshold is set at minus 38. If it's below minus 38 on the input, he's going to return to 0 and drop all gain control. That's kind of nice. That actually sounds a little better than just the old-fashioned expander. He returns to 0. How do you like the gate mode? Is ooze or hold? Ooze. I'll tell you what, I guess real engineers use the ooze setting. All right, let's do. Then we get the stereo generator. By the way, don't ever hear that. You'll blow your listeners' ears out. I'm kidding. That's a test time. You can see that. You see your various adjustments here. SCA inputs. Digital output level, that's if you're driving AES, which I am. I'm driving a broadcast warehouse. This is actually for one of our translators, one of the AM translators. So I'm driving a broadcast warehouse or a BW broadcast. Gosh, I've forgotten the power. But anyway, it's a smaller unit, and this thing just works like a champ. Here is something that the newer models will do that you're going to love if you have an FM. Multipath limiting. You know, there's the old salt says that stereo is worse on multipath, which it is. What you can do is this multipath limiter is a smart control circuit that actually blends the high frequencies together in certain situations. They explain it in their documentation if you want to read up on it. A lot of it sounds like witchcraft, but I'll tell you what, it is surprisingly effective. You can cut off the multipath control, drive around in the city, and you'll hear multipath at intersections. Cut this on, the multipath is greatly reduced. And it does that by blending the mono when it can get away with it, but only in certain bands. It doesn't do it across the board from bass all the way up to high treble. It only does it in bands that it think are going to cause trouble. Okay, we don't need to look at the system. I'm glad I remembered that's one of the main reasons I pulled this up. I wanted to show that to you. All right, composite clipper drive. That's obviously, as it says, that's how hard you're driving the clipper. Then you set your output levels for the desired modulation. Incidentally, you may notice that I'm not driving that clipper very hard at all. I'm on the 0 dB. I'm just letting it catch stray peaks. But if you watch down here, even on voice, you can see every now and then I clip, sometimes very hard. See that one? Quick little clip that made it through the processing sections. My goodness, it's already 47 after. All right, let's go back to the Zooms. I'm still getting the hang of this. All right, I want to go back to Zoom. Give me Zoom. I don't like you anymore. Here we go. Well, I'm just going to close that for now. All right, screen sharing has stopped because I killed the screen that was sharing. What was that about my mic? Anthony, I was picking on you. I said real engineers have microphones. You're still my hero, though. Anybody who can handle 64 signals has got to be a guru. I mean, I'm sorry, you are. You're just a guru. So there you go. You realize it is fun, Harry, that he can't talk back to me.
We like to pick on Anthony when we go to the conferences anyway.
Good for you. All right, let's see. There were a few other things we wanted to mention, or let me look at the chat. Does anyone have any questions? I'm going to switch to the gallery view. Anybody have any questions?
Does it work now?
Oh, my goodness.
What about logging over a period of time?
What do you mean by logging over a period of time?
Like throughout a day, do you log, which are the loud parts, which are the quiet parts?
The more expensive processors will do day parts. You probably know that. In fact, if you're giving me just a minute. I don't know why this thing's being so ornery. But Anthony, I'm so proud of you. You got your mic working, man. You're fair.
Well, my other computer was behind a VPN, so my PTP clock wasn't working.
Hate when that happens. All right, I'm connecting to a different processor here. Well, see if I can pull up an Omnia 11. But they named it that on purpose. We go to 11. Yeah, sounds good. All right, here we go. Let's see if I can find that for you. The one other drawback on these top line processors is that these top of the line processors, the problem with them, of course, is that they become much more difficult to adjust, but you know that. Here we are. Let me see. I think that's under, see if it's under, no, it's not under output. It's under, it's got day parting in it. I'm going to have to find it. By the way, I mentioned yesterday, I mentioned in the last session that, people are going to think 10 dBs is twice as loud or twice as soft or half the volume. So you may righteously wonder, well, if that's the case, then why will changing a few, like 1 or 2 dBs here, make a difference? Remember that in this case, you're changing the drive into a state machine that has a fixed limit. Another way of looking at it is you've only got 100% worth of modulation to play with. So if you pump a lot of bass into it, you're stealing that much from everybody, from the other channels. It's the same if you decide you want to be the brightest thing on the dial, so you kick up your audio at 10 kilohertz. That's fine. You're going to lower your overall volume because you've only got so much modulation to work with. In this case, you are changing the drive levels into an extremely complicated machine. Well, I don't know why it's not showing me details when I've got full access. I think he hates me. Let's see, there's our presets.
What was that software update you skipped?
Yeah, it very well could be. These are the kind of things that I set once and then leave alone. How do you like, I'm using 1.1 dB of solar plexus. Take that, competition. And I love, they've always called it fat bass. You'll see I actually pulled that down a little bit. And the reason I did is because we were kind of chewy sounding on our particular music. I am going to add 1 dB back, and then what I'm going to do is spend time listening today and see what I think. I did add 1 dB. That was, by the way, the default preset that I built on. That was set to like 3 dB, which sounds great on some formats. On ours, we sounded like the world's worst boomy. It was just horrible. Deep bass. Punch mode is low. We try not to punch people. Deep bass slope. Make here on all of these, make small changes and then listen for a while. You can go look at Frank Fode's recommendations. You can look at the Wheatstone recommendations, at the Orban recommendations. Every one of them are going to tell you this. You make little changes and then listen. Find a preset that is close to what you want. That's close to what you want, which we're not doing any of the salts. I don't know why they're still in there. And then make very, very fine tweaks. I'm going to go ahead and save that change. I've added 1 dB to the fat bass, and I'm going to see what it sounds like. By the way, I remember Anthony mentioned something about what do we do with noisy signals. I've thought long and hard about that. You can try. There are some active noise correction boxes you can buy. There are some active noise correction plugins. But basically, I stand by what I said before. You've just got to make sure your audio is good as possible before you put it in. I mean, there's really no other way around it. The kind of thing that, like using noise correction can work, but it's not going to be an absolute miracle worker. Even though the first time you listen to it, you're going to think it is, or you might think it is.
So I got a question.
Who does?
Anthony again.
Hey, Anthony, what's up?
Never have problems asking questions at these things. So
I don't care. That's what I'm here for.
So my curiosity is about compression into compression into compression into compression. So there you talked earlier about the fourth dimensional problems of timing and losing that information details. So a lot of playout systems, your cart systems, et cetera, have normalization on top of them. Then they go through a console, and then, of course, some normalization is applied to on top of that. And by the end of it, you just have this soup of transients that finally hit your broadcast processor there. What kind of recommendations do you give for people who are adjusting and treating this as a chain opposed to as just the last stop in the proverbial dumping ground of signal?
Once again, there is no perfect solution. I'm serious when I tell you how. I'll just tell you how we handle it. We use tamper shields. We tell people keep their fingers off. Anything I have at the studios, any compression or limiting I have at the studios is very gentle and is only designed to prevent overloading an input. For example, on STL, although we are getting ready to. We're getting ready to upgrade to, we're already using AES on all of our STLs. We're getting ready to upgrade to WheatNet, to their audio over IP system. So, and by the way, Wheatstone also has, I know what you're talking about. We have the Wheatstone blades that we use in our audio over IP networking. Each blade has several built-in Voices processors. And the first day we put that blade on air, without thinking, I had that Voices on a very mean preset because I had been playing. I was listening. and I left that preset on, and then it goes out to the transmitter side into a Voices Era 3. We sounded like a 1970s top 40 AM station, and not in a good way. That was the loudest station you've ever heard. Anthony, I don't know what the answer is. You have to train your personnel. You have to keep an eye on all the processing there. You are going to get audio in from other sources that has already been badly compressed. I showed you that last time. Some processors have what they call declipping, and they try to correct for some of that. So there you're going to have to spend money and buy a really good processor, and that's going to be top of the line Omnia, top of the line Voices, or something like that, that specifically has declipping, decompression, and correction for things like that. There's Anthony. What's up, my friend?
So I even brought out they gave me the CBC mic. They're like, hey, you can take that. I'm like, all right, I'll take one. So, it got burnt by a light, though. You can see.
Well, Harry, I think it's probably about time to wrap up, isn't it?
All right. Well, if anyone has any questions, ask now. If you think of anything, do send us an email, and we'll make sure they get forwarded to Stephen. And we'll see you all in 2 weeks. All right. Take care, everyone. Enjoy your weekend. And Stephen, enjoy down south with those really warm temperatures.
Yeah. Have a good one.
Thanks for coming, everyone.
Thanks, Stephen.
Hope to see you in 2 weeks.